All right, this video's topic is linear dependence and independence, and that's in reference to vectors. We're looking at independence and dependence of vectors. So, what's your goal today? I can explain the difference between linear dependence and independence. So you're able to explain the difference, and then you can successfully apply skills to the appropriate problem. So you can actually take a problem and determine whether we're dealing with dependence or independence. So linear dependence of two vectors. So two vectors called u and v are linearly dependent if and only if there are scalars a and b. So this is not the word a. So scalars a and b, both non-zero. So that means they're not zero multipliers, such that au plus bv equals the zero vector. Okay, so we have linear dependence if we can create the zero vector. So two vectors that do not satisfy this condition, so the ones that do not, are then by definition independent. So going with a diagram on this, linear dependence. If I can create the zero vector, the only way I can create the zero vector with two vectors is that they have to get back to my starting point. So if this is my vector u, and this is the starting point, the only way I can get back to that point is if the v vector is either parallel and can be turned around with some scalar multiple, or if I have the u vector and the v vector, and they're collinear. So parallel or collinear. So I can take those vectors and I can turn them around such that I can get back to my starting point in both cases. All right, so you need to use both vectors, and you need to be able to move away with the u vector. You need to return with the v vector for linear dependence. Okay, and those are the two conditions right here. They need to be either parallel or they need to be collinear. So on the flip side, linear independence simply means that our two vectors, if I'm on vector u and vector v goes off to the right, I cannot move those vectors around. I can't take the v vector here and move it to get myself back to my starting point. So these are linear independence, is when you have non-collinear or non-parallel vectors. All right. So there's linear dependence and independence in two space. So dependence, you can get back to your starting point. Independence, you cannot. You'd have to create a new vector to get from head to tail. So what happens if we move to three vectors? So we have now vectors u, v, and w are linearly dependent if and only if there are scalars a, b, and c. So we're talking about linear dependence. And again, linear dependence means that you can get back to your starting point using the three vectors. So we're looking at a combination where au plus bv plus cw gets me to the zero vector, returns me to my starting point. So ones that do not satisfy that then are obviously the converse. They're linearly independent. So quick diagram with that. Linear dependence. So we're looking at three vectors that would allow you uv, let's put w in this way, that we could rearrange them such that they would form a closed triangle. So it can be arranged, can be rearranged to form a closed triangle. So for the diagram I drew, vector u and I guess v would have to go this way and w flipped around so that we would get back to that starting point of u. Okay. Now going back to my diagram for a second up above here, what does that mean then? If they can get from starting point to end point, that would be like getting directions on a map. And if you're on a map, you're on a piece of paper. So that means all three vectors would fall on a piece of paper or on a plane. So that would then mean all three vectors must be coplanar. All right. So you need to be able to get back to your starting point or form the closed triangle. So the flip side, linear independence, means we got one vector that takes you in such a direction that you can't return to your starting point. So since we know that a plane's involved here, if I had vector u on the piece of paper, and I had vector v on the piece of paper, but then had vector w heading off the piece of paper at some angle, then what would happen if I started at u, and then as soon as I use vector w, I'm off the piece of paper, and v won't get me back on that piece of paper because u and v are coplanar on the same piece. So w takes me off the page or off the plane. I can't return to the plane because neither u or v will bring me back. All right. So that would mean that u, v, and w are not coplanar. And just tying it into the previous lesson, u, v, and w, all vectors, are a basis for space. And w are a basis for space. Okay, so linear independence is when you cannot return. The only way this would work is the multiplier on both v and w would have to be 0, so it would end up looking like this. The only equation you could come up with would be u plus 0v plus 0w equals the 0 vector, which means I'd also have to multiply u by 0, and that's the definition of linear independence. All right, so there we go. So how is that applied? So I got a couple of examples running through its application. So the first one here, fairly straightforward, just in terms of the explanation, and it kind of supports what I was just talking about. So we're supposed to assume the vectors u, v, and w are linearly independent. Linearly independent. So that means that we can't get back to the starting point. So in your head, you know that 0u plus 0v plus 0w is equal to the 0 vector. So when we look at the example here, this coefficient or multiplier or scalar value has to equal 0. So 2a plus 4 equals 0. Solving for a, we find that a equals -2. We find that b minus 3 has to equal 0. So b equals 3. So remember, the coefficient is the expression in front of vectors u and v. So therefore, to make this a linearly independent system, a is equal to -2 and b equals 3. And that would make that expression, 0. It would make that expression 0 to make it a linearly independent system. Similar approach or process on the bottom one here. We know that a minus 7 would have to equal 0, which means that a equals 7. Here, 2a minus 3 has to equal 0. So 2a equals 3. A equals 3 halves. But now we've run into an issue because now we have a variable and it's taken on two different values, which isn't permissible. So therefore, no value of a will make this system linearly independent. And if you take a note on the last one that I never bothered getting to, but for the last one, 5 would have to equal 0. We know that's not true, so there's another problem that we would run into where there's no value in order to make the system linearly independent. So in this case, with this example, you're looking for variables to make that scalar equal 0 to create a linearly independent system. So there's a couple questions like that in the homework, and examples just to help avoid confusion when you get to them. All right, and I believe the next one I need a little bit more time, so I'll stop the video here.